Hey folks, welcome. So I'm going to show you guys how to um, create different plan forms um, that you'll be able to then run in your code. So we could do several different things. We could look up different airplanes. You could look up like the plan form, and you can probably find images that way. Yep, there's one right there that we could totally use. Um, there's so many different things that you could do. Boeing 747 plan form, and you can already see they've even got some with dimensions on it. We actually don't need the dimensions, which I'll show you why in a little bit. But anywho, so you can usually find the plan form for almost any airframe or animal. So I wanted to actually do a swallow. So none of these look very good. I looked at this up earlier and I think it turned out better if I did wings. There we go. And there was a picture I had in mind, and it's this guy. Okay, so let's go ahead and save this. We can save it anywhere. Swallow plan form. We're going to save it to our desktop. So now we're going to use something called Web Plot Digitizer. Oh, come on. Digitizer. Whatever. So this is a great little tool that you can use to read in a plot and determine the values from it. You guys have seen the benefits of this already. Just from like the cylinder data we did on exercise set, oh golly, 3 or 4, I believe. Maybe it was 2. I think it was 3 or 4. But those were pulled off of a plot from a I believe it was a journal article. But so we just read in our image, and we're going to do a 2D XY plot. We don't need to worry about the other options. We're going to align the axes, and this kind of gives you some directions. You can go through and read it on your own time. But we're just going to stick in a few different points along this wing. Specifically, I'm going to do it at the wingtips and at the center of the fuselage, or in this case, the center of the body of this swallow. And let's see, those look like they're about even. Let me see. Yep, 235.24, 235. Well, it doesn't really matter all that much. Okay. Now, so we're going to put in some values, and we'll come back and fix this in a minute, but the x value we're going to put in, let's see, 0.1 aerodynamic coordinates. Out the left wing is positive, right? So we're going to do a positive 0.5, and out the right wing is going to be a negative 0.5. We're going to leave the y-axis for where it's at for right now, and we're going to come down here to measurement, and we're going to measure the wingspan on this image, and it's going to tell us in pixels. So we've got 390.77, and then let's do another one. Here, I'll write this over here. We've got 390.77, and then we're just going to measure the root chord of this airframe. Is it going to let me? There we go. Got to add a new distance. Okay. And it doesn't have to be perfect, you know. This is already going to be pretty guesstimatey. 70.09. So let's do 70.09 divided by, and what this is going to do is this is going to tell us the aspect of the root chord divided by the wingspan of whatever airframe that we're looking at. So there we've got a value right there. So this tells us basically our root chord, our C root over B. Now, since we're going to do it as from 0.5 to negative 0.5, and you don't have to do this. This is just going to make it a little bit easier, I feel, in the long run. And so we're going to stick the, let's see, we're going to do 1 over 4, and that's going to tell us our leading edge value, if that makes sense. So let's go back over here and tweak calibration. We're going to just do complete because we're going to leave them the way they are. So y1 is going to be the leading edge, so it's going to be this value right here. And then we multiply it by 3/4, and that's going to tell us our trailing edge value. Technically that should be a negative, right? But, okay. Okay. Alrighty, awesome. Okay, so we've got those values in there. Okay, so now that we've got our plot in there, we've got our axes aligned, what we're going to do is we're going to add a data set. And this data set is going to be so that we can pull off the leading edge and the trailing edge of whatever this wing is. And that's just to get rid of the sweep in the wing or other characteristics that we won't be able to model in our code. So I'm just going to put points along the leading edge of this swallow, and try to space them out so it's an okay, and we can kind of fix things by moving them like that. Okay, there we go. That looks okay. I'm going to take a look at this one because it looks like it doubled up. I'm not going to delete that one. There we go. Okay, cool. All right, so let's go over here to data sets. Let's rename this data set. We're going to call it LE, and that'll make it a little bit easier later on. Okay, let's add a data set, and we'll call this one TE. Okay, and let's change the color just so it's a little bit easier to see. I'm going to make it blue. Okay, so now let's go over here to, okay, oops, there we go. Okay, so now we're going to add the trailing edge data. So we're going to try to go somewhere in the middle of this fuselage. We want to pretend like this wing goes into the fuselage, and that's actually a pretty good way to treat these type of things when you're ignoring the fuselage like that. We will be able to determine the lift a little bit better by assuming that we're basically inside of the fuselage. Our wing goes into the fuselage, and that's just to increase the validity of our results. So I'm just going along here. It's not going to be perfect. Fair enough. And let's see. We'll go along here. Let me go down. Let me make sure that's on there. It doesn't matter a whole lot. Okay. Now, if this wing were just like a single tapered wing, it would be pretty easy to then just take these results, go to some sort of a Google Sheet, and just pull off the data. But because we have these points and they don't line up perfectly, especially right here, it's in the middle of this region, we're going to have to interpolate in order to determine this Planform. So now let's save our project. So we've got all the data, and let's save it as swallow. Let me think, plot digitizer, and we'll save it as a JSON. Okay. I'm thinking we might have messed ourselves up because we did the right wing and we assumed that that was negative. So I'm going to cheat, and we're going to cheat a little bit. We're just going to flip this guy. Make that negative, make this positive. Okay, and so that's going to make it so these guys are positive. Let's see, we'll go down here, save project, download it, and we're going to move this back over here and replace that file. And that's just going to make our lives a little bit easier so we don't do. Okay guys, sorry, I don't know what happened there. I was recording and it decided to not record the screen that I was sharing. So, I'm just going to go over to where we're at right here. So I went back and I reloaded this data. I flipped the axes. I made it a negative. I made it so that it was, I flipped the signs of the 0.5 and the negative 0.5 back in the tweak calibrations. You guys can go back and look at that. And so, and then I started writing this code. So we're going to need NumPy, we're going to need JSON, and you can see how I have it set up right here. We're going to read in the JSON file, we're going to get the points from the file, we're going to have some array, some dictionary for our dataset collection, and then we're going to step through this dataset collection and pull off the leading edge and trailing edge data points. And so you can see how I have that here, and these are formatted so they'll be the same way for every plot digitizer file. So if you wanted to do multiple planforms, you could. So here we've got the leading edge data, we've got the trailing edge data, and let's just print those off just so you guys can see what we're dealing with. So I'll go over here, CD code, CD aerodynamics, CD GI, CD wing. Okay, Python make planform. Oops. Make planform file. Ooh, that was fun. Let me try that again. CD arrow. Oh, code. Code arrow GI wing Python make planform. Okay, what's going on here? LETE. LE index is not defined. Oh, it's because I'm setting them. I should be assigning them. Okay, there we go. Okay, cool. So we've got our list of z over b values for the leading edge and x over b values for the leading edge. And then we've got our z over b values and our x over b values. So a couple things you'll notice is that we've got a 0 value, or a value that's not quite 0, and a value that's not quite 0.5. And then over here we actually have a negative value and a value that's not quite 0.5. So won't matter whether we change this last value to be 0.5 or not, but it will matter whether this guy is 0 or not, because that'll mess with our code. So we'll go ahead and force that first value and the last value to be 0 and 0.5 respectively. So we're going to force 0 and 0.5. So we're going to do LE, the 0th row and the 0th column is going to be 0.0, and we're going to do the same thing to our trailing edge. Oops. And then we're going to do it for our last row in our 0th column. So -1, that's just our last row. Okay. Alright, so now we're going to collate and sort the z over b values. Alrighty. So we're going to do zb's is equal to np.unique of np.concatenate. And we're just going to combine the z over b values for our leading edge and the z over b values for our trailing edge. Okay, and now we're going to calculate, determine leading and trailing edge values. Yes. So we're going to interpolate just like we would in our code. We're going to give it these ZBs, and like I mentioned before, we're just going to figure out what the leading and trailing edge values would be at the locations that we don't have a value. Okay, so we're going to give it our LE Z over B values and our LE X over B values. And we're going to do the same thing for our trailing edge. Okay, and now, pretty easy, we're going to calculate the chord. So now that we have the same Z over B values for each of these guys, we're just going to get CBs is equal to LES minus TES. Pretty simple. Okay, now we need to write this to a file. File name is equal to, well, we've actually already read in our file name output file. So with open output file, we're going to write to it as f.write, and this is just the header that we're going to give it, and we're going to tab separate these guys and do a new line. This is just the header that we're going to give it, because that's how we're going to format them. Run through and write Z over B, C over B to file. Okay, so now we're going to step through these guys, step through each Z over B value, and since it's the same length as our CBs, it's going to be okay to do that. So we're going to do f.write, and then we're just going to format them a certain way, and this is just going to make it so that we have, you know, enough digits to matter, but not too many. And then we're going to see, we're going to tab separate it, and this is just a formatter, and you can Google this. It's called Python string formatting, format of ZBS of I, CBS of I. Okay, and then as soon as that's done, we're going to close the file, and bam, we have our code. Okay, so let's go ahead and run it. That'll be fun. Only integer scalar arrays can be converted to a scalar index. Oh, it's because I didn't stick it inside of a tuple. There we go. Okay, alrighty, let's go ahead and open this guy up. Let's see, swallow Planform. So we've got our formatted file. You can see it goes from 0 to 0.5. Perfect. Alright, so let's see what this looks like. So I've got my W4 code here. So we've got file, and then we've got swallow. Oops. Planform. We're going to do a none. Let's add some rolling rate in there. So a couple things. We can change our CL design to be something that we would want it to be. So for example, for a swallow, we could say, oh, you know, it's going to fly so fast. It usually lives in this climate. I mean, they probably live in Logan, I betcha. So you could pick Logan density. You can calculate the wing area just by Googling it. You can probably find some wingspan, and from what you have from the Planform, you'd be able to back out the wing area. Let's see. I think that's everything I wanted to say about that. You can probably look it up to determine the aileron. Let's say it goes from 0.2 to 0.44. Yeah, 4.5 is fine. And then let's do something a little bit smaller on the wing. And let's say it's a little bit more efficient. because it's a bird's wing. We'll do traditional flaps. Actually, parabolic might be more accurate, but your code can only do traditional, so we won't worry about the other guy. Straight hinge line, your guys that's forced. 5 degrees angle of attack. Let's see, let's do something a little bit smaller, just for fun. Let's do an aileron deflection of 2, and we'll do a steady rolling rate. And let's look at the CL hat distribution. Okay, Python wing.py. Okay, cool. So we can see what our Planform looks like. We had 0 washout, or what the CL hat looks like. I meant to. Let's do this. So, okay, guys, I apologize. I don't know why it didn't show the figure before. Apparently Windows game recording is not working the way I thought it should. So anywho, here's our Planform. It's got our ruffled back edge like we expected. Okay. And here is our CL hat distribution. So we can look at that for a minute. Alrighty, thanks for watching, guys, and hopefully this was helpful to figure out how to do these Planforms. Thanks.